I think you can hear me. So I just want to welcome everybody here. And the reason we're in this larger venue is for the videotaping of Robert's talk, because I saw in YouTube, he goes to Cornell, and Cornell does this elaborate one-on-one interview with Robert, talking about the work he does. And it's like, oh, come on. And, you know, he went to our school. Why aren't we doing something? Okay, so that's why, okay, so this room is built for videotaping talks very easily. And so it's my pleasure to meet Robert, and I try not to think about how far I go back with Robert, because we were, I was working at Bell Labs. In fact, I remember I was just minding my own business at Bell Labs. I was laying low that summer, and this guy is knocking on my door, and he introduces himself as Robert Hampshire, and he was there as a summer student, and he, you know, at that time he was an undergraduate at the University of Cincinnati in electrical engineering, but you know, for electrical engineers in the 1990s, felt a little adrift because the internet had been built. You know, what do they do now? And then Frank Kelly was visiting us, and he was talking about internet, you know, network economy. And network economy economics, you have to look at how many customers there are and how many customers can be described by a queuing model. So the beginnings of queuing and economics, we're starting right there. And so I said nothing, and he told me he wanted to apply for, you know, Princeton's Operations Research and Financial Engineering Department. Okay. And then little did I realize the summer we worked there in 2001 at Bell Labs, when the summer was over, we would both leave and go to Princeton. Okay. And so he got his Ph.D. here at Princeton University in Operations Research Financial Engineering Department. And then he went on to first be assistant professor at University at Carnegie Mellon. He was in Pittsburgh for a few years, and then he went to the University of Michigan, and now he's tenured professor of the Gerald R. Ford School of Public Policy at the University of Michigan, and he doesn't work on telecommunication problems. He's taking queuing theory over to look at resource sharing issues in the world of transportation, and become an expert in the area of smart cities. So.
Okay, good. All right, thanks, Bill. All right, well, thanks, Bill, for the great introduction. And thanks for changing the location of the seminar. So thanks for coming over. So let me just jump right into it. So I'm going to talk about a collection of work that we've been doing over the last 10 years or so related to reducing congestion, pollution in cities, and trying to make them more livable. And so there's a broad rubric here I call data and decision sciences for parking management. This is one set of activities that my research group have been working on. And so for those of you who are going to fall asleep and not pay attention, I'll just give you the punchlines right now. So what we're going to do is a field experiment of pricing. It's a spatial pricing problem related to parking. And so we actually implemented this in the field. And basically it's a test of marginal pricing for parking. Oh, okay, let me just pull that up. So the bottom line I want to say is that, okay, for any economists in the room, so pricing works to help align supply and demand. Okay. It does work, even despite some significant market imperfections that I'll tell you about. And it actually turns out that if you can just get a few people to change behavior in a constrained system, that you can actually see a big change in some output variables. Okay, and here that is going to be cruising and congestion is one thing we really care about. So just small changes in pricing can actually make a big difference in road congestion. So I'll show that. And also, because of there's quite a bit of non-smooth behavior in some of these prices. So I'll show you that a reasonable supply and demand curve for a city over space actually has pretty big jumps in what the equilibrium prices look like. So you can be on one block and the best price is $5 an hour, but an adjacent block literally will be 25 cents an hour. That's the right equilibrium price. And so you get these sort of very non-smooth set of prices. I'll talk about that. And then finally here for cities, think about on-street parking. Really, cities oftentimes think about occupancy, how many cars are parked. But that's really not the right thing to look at. I'll show you that what you want to look at is from the perspective of the driver. What's the chance that when you show up to park, there's a space available? All right, and a lot of cities actually look at the occupancy of spaces, but I'll show you that's not necessarily the right thing to do. Okay, so these are some punchlines that I'll return to hopefully soon. So, and like I said here, the idea is that a little goes a long way. So what we're going to do is modify prices in some very elaborate way, and it actually turns out that the occupancy changes only 1 or 2%, but that corresponds to roughly a 50% decrease in the amount of time it takes people to look for parking. So this is the idea of this sort of congested system. You can really make a big impact by small changes on the inputs. So of course, idea of pricing for roadways is not new. Actually, even pricing for parking is not new. So Vickery back in the 50s actually has a whole paper about parking and using congestion pricing related to on-street parking. So, like I said, this is part of a larger set of activities we've been up to. I'm not going to spend much time. We're doing some stuff, AVs. We're looking at travel behavior impacts of on-demand mobility. A lot of stuff now on socioeconomic impacts of automated driving systems and driverless vehicles, and a lot of stuff about financing of smart infrastructure. So that's like real options and so forth, blockchain and stuff. So I'm not going to talk about that. We also have lots of stuff going on in bike share, scooter sharing, alternative modes of vehicle ownership and so forth. But I'm going to focus just in the top left corner, the smart parking. All right, so let me just jump into the motivation. So, all right. So of course here, road congestion is certainly a big, some people think a waste of time and annoying. It's also a signal of economic activity. But it turns out that, of course, you guys know lots of cost is attributed to people sitting in traffic throughout the day. 9% of all driving time is actually spent in congestion. So-called 42 hours a year spent sitting in traffic. And this comes at a huge, $300 billion cost of congestion. That's lost wages and time mostly. But guess what? Even though sitting in congestion is really annoying and costly, we all still do it, right? Because we want to go to work, we want to see our friends, and so forth. So with that setting, it turns out that, we still do it because we don't pay the full cost of the externalities that we're imposing on other people. So it's sort of the herding behavior, tragedy of the commons idea. All right, so we don't really pay our full freight. Some estimates that roughly about 8 cents per mile is actually the cost that you impose on other people due to the congestion that you cause. There's certainly a lot of noise. There's a safety risk per mile that you impose on other people that you can kind of estimate. This is from the literature. and certainly pollution risk. This one's a little more wonky because, well, how do you price pollution is an issue, but you might think about that's a cost externality that you're imposing, that you're not quite internalizing. So, but it turns out there's even more cost that you're not paying for. Because guess what? Most of the time you park at the mall, you park places, you park for free. But guess what? Those parking spaces aren't free. Certainly there's a cost that's attributed for every trip you make in the city. There's a parking space waiting for you on the other end. There's some cost associated with that. And also the cost to build. If anyone's priced out prices of garages. I mean, there's a lot of municipal finance in cities that take out big bond issues to pay for parking garages, to build space. So it's certainly not free. So you don't really pay the full cost of either your trip when you're driving or when you park. Those are all subsidized by other actors in the system. So as you guys know, I guess this is resurging in New York, right? But congestion pricing is one way, theoretically, to think about ways to get drivers to pay for some of the externalities they're imposing on other people. Of course, Singapore and other places have done this for a long time, and they probably have the most pure form of this congestion pricing because they can do it at the roadway level. And the idea is to try to have drivers pay for this marginal cost. But of course, with other versions, there's political backlash to this. I guess I haven't kept track today or the last couple days in New York what's happening, if they're going to move forward or not. But certainly 10 years ago, when this came out the first time, there was certainly major backlash about congestion pricing. And cities like London have a version, and this is what New York City is considering more like cordon pricing. This is when you enter a region, a congestion region, you pay, as opposed to the pure sort of Vickery prices where you're being charged for the actual road segment that you're going to travel on. That's sort of the first best kind of idea, that you want to charge per link. But there's other approaches that do this sort of cordon pricing and so forth. So let me get to parking. Okay. So one way you can think about parking pricing is actually an alternative to road pricing. Okay, so one way to think about it is that, okay, every trip ends with your car parked somewhere. All right, so you may think about parking pricing as some kind of so-called second best approach to try to capture some of the externalities related to driving. Okay, so there's a body of economic literature that conceives about the price of parking in this way. If parking's $1 million an hour, guess what? You're not going to go drive and park there. So you're controlling traffic congestion. Okay, so imagine there's some price between $0 and $1 million that might make sense. Okay, so that's how we're kind of framing this. So, but the idea, what is that right price? And so in some ways, you might think of the price equaling the marginal social cost for occupying a space, right? And so this includes the cost, the searching costs that you impose on other people while you're driving around looking for a parking space. You're inconveniencing lots of other people. Maybe you should somehow internalize that. Certainly the safety risk, the pollution risk, and other costs, you might want to try to capture that as well. And so, for example, I think this was in London, that roughly estimated about every hour that you were parked, you caused about 3 to 4 other people to look for a parking space. Okay, and there's some time costs associated with that. So this is some of the sort of the empirical foundations we're thinking about parking pricing and a way to frame it as this congestion charge. So, but I want to say, a lot of the ideas about congestion pricing, like be it parking or road pricing, assumes a lot about people's knowledge and information flow. For example, you assume it that, okay, one, drivers are making rational decisions. Okay, so we know parking sometimes is irrational. Some people think they can always beat the system. Most drivers, for example, think they're better than the average driver. And some people think they're better than the average person at finding a parking spot. So they'll have these risk behaviors that, so there's a question here, okay, do people actually make rational choices about looking for a space? Alan, I'm sure you're good at finding a space better than anyone else. I can imagine. One, that people actually pay for parking. Okay, pricing only works if people actually pay for it, And then also, in a lot of places, you have a lot of visitors who don't know how much parking costs, so they're not making their decision about whether to make the trip, based on full information, or where in a given city to park, at what price as a mechanism. Like, for example, does anyone here know how much does it cost to park on street in Princeton, say on Nassau Street, per hour? $2.25. Oh, very good. Okay.
Oh, no, I mean, they just changed that. It's like $8 or something.
It's $8 now?
I don't know.
So that's what I'm saying.
They just put in new stuff.
Yeah. So,
We're going to do it based on time and mayor, whatever.
yeah, so a lot of this foundation depends on, do people actually even know the prices to react to them? And that's the same for road pricing. And you assume it's enforced. And so okay.
It's perfect in Princeton.
Oh, enforcement is perfect. That's true. Okay, so here's where, let me get to the meat. So what we did is, this was part of a $20 million federal pilot program. I think that was matched by the state of California, so like a $40 million pilot program in San Francisco to actually implement a dynamic pricing scheme for parking that with the goal is to minimize the road congestion associated with people looking for parking, and also with the goal of improving the vehicle speed and flow on the roads. So what ultimate goal of reducing greenhouse gases, like localized pollution that's related to people looking for parking and congestion, and improving the traffic speeds. So the way this program worked, there was one part of it that was we call it so-called demand responsive pricing. The other, as you see here, and it looks like they did this now on Prospect smart meters. So you rip out the old meters and then you put in so-called smart meters, or you allow people to pay by their cell phone or something. So we did that. Here, longer time limits. So a pure market-based approach for parking would actually have no time limits. You would just use price as a mechanism to, so it's like supply and demand. If you want to park longer, that's fine, but you're going to pay for it, And the other part was the information environment. So this is the real-time information environment. And the way this was actually implemented, this was implemented in certain sections of the city, that's the orange, and then other parts of the city it wasn't. So it's like a quasi-control. So this is kind of try to control for macroeconomic kinds of activity. So, when the economy's bad, people aren't going to work, so congestion's down, right? So what we wanted to do is have some areas where we didn't control the price, so then we can try to net out the effect of the pricing.
What's the difference between the orange and the blue?
So the blue are the areas we didn't change the price. Orange is where the intervention was. I can tell you more about that. Okay, let me just say that this is joint with some collaborators. We were actually on the technical advisory committee to the city to set up this program. And with someone else named Donald Shoup. Okay. Yeah.
If I drive round and around and pretend I'm looking for the pricing, can I raise Alan's?
Yeah.
Is it open to innovation? What's your
Yeah, so I'll tell you. So here, I'll tell you the pricing is not what I call like dynamic pricing. It's not a real-time changing price. We're only going to change the price once every 6 weeks. So it's not like you pull into a parking spot and then then you know the price. So because there has to be some price discovery that affects people's behavior. So they need to kind of know some predictability about how much it costs. So that's, so no. Your answer is no, you can't. No. Okay, so, and I'll say this later because we had to get this past city council. So the pricing mechanism had to be such that it was understandable. Okay. So here, what I want to say is, did this program actually increase parking availability and reduce search times? That's sort of the key question. So in some ways, it's like a program evaluation. We created some algorithms, implemented them in the field. They were in the field for about 4 years. And then we want to say, have they achieved their goal? All right, and so again, the two main pieces of this time of day pricing and this real-time environment. So actually I had students who built the first version of this app that has real-time information about parking. And then the city turned out to use that in the full implementation. Again, like I said here, it turned out that, as you see here, the control and pilot areas, there were roughly about 6,000 spaces. These are on-street spaces that we actually we had control of changing the price of parking. So here, what we did is we wanted to adjust the time of pricing by time of day. So the way this is set up is there's a morning price, afternoon price, and an evening price. Okay, those are the three. So it's not like a continuously changing price, it's just morning. And the idea, so I put this paper down here because this is actually a paper for my dissertation. So this is how I got into this. This is how do you set, this was actually in a telecommunication network. How do you set the price such that when someone shows up to use the resources, there's some guaranteed probability that there's a resource available to use it? That was a chapter in my dissertation. So this work, years and years later, turns out to not use that, by the way. I mean, this is really theoretical and not so practical for implementation, but this informed what was actually implemented. Okay, so we boiled down the objectives to this. The idea is that for each block, we want to keep the occupancy between some band, 60 to 80% full. All right, and because that way you're utilizing the block, mainly people are traveling for some value-added activity or some utility. They're shopping, they're seeing their friends, so you want to make sure there's space available. But you want to make sure there's not too many spaces available, right? And so we actually shoot for this band about 60 to 80% full, okay? And the way the pricing algorithm works is this. So in the previous 6 weeks, we observe all the occupancies on all the blocks in the city. And for each block we look, over that previous 6 weeks, was the occupancy over 80% full? If it was over 80% full, then we just increase the price by a quarter for the next period. So increase the price, maybe discourage people from parking there because we want to pull it down between the 60 and 80% range. All right, but if in the previous 6 weeks the occupancy is lower than 60%, then we lower the price. Okay, now here's the part where we have a nice theoretical model of how you should change the price, and it's really, but the people implementing this in the city were like, okay, look, give us something that we could actually make sense of and communicate. And so this was it. We could only increase the price by 25 cents per hour, but we can decrease the price by 25 cents or 50 cents. They were fine with us decreasing the price. It's the increasing that's the problem. Okay, so the idea with this, you're not supposed to really try to read that. It's just to show that there's a flow of algorithm. And so this, like I said, we do this over these 3 time bands: morning, evening, after lunch and evening. So let me get to the punchline. So we had this pricing scheme, and so like I mentioned, one of the key assumptions a lot of time in revenue management or pricing is that the users or people actually know the prices. And so the city did a major marketing campaign. So this is from the San Francisco Chronicle. And there were billboards all over the city, at bus shelters, a very large campaign to let people know that this program's happening and that there's an app available. On that app, you could see the prices in real time and so forth. So it was a big effort to communicate the prices. So the way this worked is, for example, and here's the Fillmore area. So here, the brown area, for example, is where there's low occupancy. Okay, so, and red means the occupancy is high. All right, so here's the sort of a before picture. And if a block is between, less than 60% full, then we decrease the price for the next time period. So here are the corresponding price changes. So green in this picture means we decreased the price on those blocks. Red means we increased. Okay, so we looked at the previous time period, look at the average occupancy, then we changed the price, and then we see how those prices affected occupancies in the next time period. Okay, so here, the idea is we want to move more and more of these blocks into the blue area. So this is how the program works.
Why did you increase sometimes the red street?
So the red should only get increases. Hopefully the red should only get increases. If in this time period you were red, then you should get over here increases. So over here for increase. Yeah. And the idea is to push everything into the blue areas. Okay, so here is sort of a net changes over the different neighborhoods. So this is over 12 price changes. So you can see on net, red means on net that the price increased. Green on net, the price decreased. So we did this is after 12 price changes with 6 weeks in between. So you see here, it's not really like a price gouge. I'll call it. There was a big backlash to this program, like, oh, the city's just gouging us for more money, revenue. All right, and so you see a mixture of green and red. So some areas the prices decreased pretty significantly, and some areas it increased. Yeah, there.
How transparent is the price? And do people have to stop and look at the meter and read the fine point, or
Yeah.
fine print, or are there big signs that say this block is this
Yeah.
much and this block is this much?
That's a great question. So it's in the app. So if you, before you leave home, look at the app, you can know what the price of parking is. If you travel to that area often, you can do some of your own price exploration. And so maybe after 6 weeks, then you understand you've done enough discovery. That's kind of the premise, why we exogenously change the price every 6 weeks. We just say we do that. We don't necessarily optimally time when we should change the prices, for example. But that's a great question. Yeah.
How much did it take people to react to this? And did the process stabilize after?
Yeah, so this is a great question. I'll get to that. So that's the question about stabilizing. Do these prices stabilize? So let me just say this. So actually it turns out that the prices were quite insensitive to price. I mean, the parking levels were quite insensitive to price. I'll say more about that in a second. But actually it turns out 1/3 of the blocks monotonically increased, the price increased this is over a 12 time change period. So they went up. 1/3 went up monotonically. Another third monotonically decreased. So your area just got cheaper and cheaper and cheaper. Some areas got more expensive. But then everything else in between actually bounced around. Sometimes they go up, then they go down. So you get some odd behavior there in the equilibrium. And also what I said, this non-smooth spatial prices. So you'll get literally streets, blocks right next to each other that have very different prices after many changes, after many price changes. And that has to do with maybe like amenities, where restaurants are versus where they're not. But you imagine people's walking utilities should be smooth over space. So it should be a nice spatial thing. So that's still actually a current mystery that we're trying to look at for spatial pricing. And it turns out the average revenue per meter went up. Okay. Yeah.
So I guess are 1 and 2 related? That
Yeah.
This looks like an area where I should increase the price. I increased it, but nothing really happened. So let me do it again.
Exactly. Yeah.
Okay.
Yeah, I'm not going to go into it. We have a whole set of methodologies how to estimate this price elasticities. It turns out it's not easy to do because there's some issue with reversion to the mean. If you guys want to know more about that, I can say more about that later. Okay, so here the idea was we observed that the occupancy and the cruising levels actually had changed, but it was actually due to our inner program, or was it due to some other thing that was happening? And so to do the actual analysis, here's what we did. This program had an API, or we had access, since we were running it, we had access to data over roughly a 2-year period about the average occupancy on all the blocks. Like I said, there's about 400 blocks in the program. 250 were in the pilot, 55 were controls. And just to kind of give you guys a sense of how much parking is, so the baseline before we started the program was $2 an hour. $2 an hour to park, okay? And so for all the blocks, we have the occupancy levels and the prices. And that's from the parking spaces perspective. All right, so this is what the urban planners and the transportation planners were thinking. They were like, oh, the idea is to kind of keep the average occupancy between 60 and 80%. Well, in this case, 85%. It was sort of in the literature. We want to have occupancy on average around 85%. And they thought and they used that as a rule of thumb. But it turns out that just because a spaces occupy 85% of the time, that's not the same thing as saying, as a driver, when I show up to park, that there's a space available 85% of the time. Okay, this is sort of different between the spatial average and the time average. So what is the experience of the drivers? And so this is, okay, some queuing theory comes in. This is a standard problem in queuing theory that it would C here a little bit be the number of spaces. You have some folks who are arriving to park. If the spaces are all full, then here you drive around in circles until you can park. Very simple model of parking. All right, and so it turns out that that's a standard. If you assume things are exponential, Poisson arrivals, exponential amount of time you wait here, there's a very standard model, multi-server queue model, and it actually turns out that from the driver's perspective, the probability that when you show up to park that there's a space available is the so-called Erlang-C formula. So you can write that down. And from the parking spaces perspective, this is the fraction that are going to be occupied in the long run. So this kind of gives you that dichotomy. So here's what we end up doing. The data that we originally had, I told you, is hourly averages. But what we did is we took finer grained observations of how many spaces were available. Okay, so every 5 minutes, we're collecting data for every block, how many people are parked there. Okay, and I'll show you why we do that. So here, it turns out that, so we want to ask, what's the relationship between the hourly occupancy and the probability of finding a space? Like I said, that's the Erlang blocking formula. But we have lots of data, so can we actually empirically verify or fit that? So actually what I end up doing is taking that Erlang blocking formula and taking the log of it. Okay, so if you take the log of this Erlang blocking formula, you can get a linear regression. So basically what I'm going to do is make like a linear model. All right, so now I'll show you why I'm doing this. So on the right-hand side are data that's related to what the spaces see. These are like the spatial averages. But on the left-hand side is actually the driver averages. Okay, so I'm basically linearizing the Erlang blocking formula and then running a regression to get a model. So it turns out that, like I said, we had about 130 observations for every block, 130,000 observations. And so you can actually fit an empirical model from the data about how, if a block is 80% full on average over an hour, what's the corresponding over there probability that a driver finds a space? Okay, and of course that's modulo the number of spaces on that block. So if you have a really big block, and it takes a really high occupancy for the users to experience it full, right? If you have a really big block. So that's going to come in handy later. So let me move on. So next, the idea is that how does this hourly occupancy data that the city uses, how does that map onto cruising? They're searching for a space. So the idea is that you're looking for a space to park. If it's not available, then you go searching around. Okay? And so what we do is a very simple model, because we don't have sensors that track all the cars in this study. What we do only have is we can only see what's happening at the space. Is it full or not? And we can see the dynamics of how the block changes. And so we're going to use that to infer how long it took you to find a space. Alan?
Don't you have an app? Isn't the app on, and then you turn on the GPS receiver, and you know everything about me and how many times I went around, or
No, we don't.
oh, you didn't go there?
No, we didn't. We should have. We didn't do that. We do have how many people are actually using the app, but we don't track the user. We should.
That's why you didn't?
I know, yeah.
You're moral.
And there's privacy reasons.
Never mind.
Now, we have other work where we actually, in the same period, purchased a large set of GPS data for about 1 million trips of people moving around in San Francisco, and we estimate how many people are excessively looking for parking. So someone else collected the data. So you can buy these data sets, as you know. So for this work, what we did is a very simple thing. Is actually just an absorbing Markov chain. I'll show you. So the idea is that you assume that each driver wants to park in a given block. They start there. With some probability, there's a space. If they can't find a space, then they move to an adjacent block with some probability and try to find a space again. So it's almost like a geometric kind of trials. And so let me show you, okay, I'll show you this. You guys know that, okay. So you have a transition matrix. So the idea is that the first row is where you want to park, where you actually are a driver and you end up parking. But let's say you start at block number 3, where probably 0.8, 80% of the time there's a space available. If there's a space available, you go to row 1 and you park, you absorb. So it's a simple absorbing chain. And so we know they're just simple linear system that can solve for the expected amount of time it takes you to park. So this is a very simple model. All right. Now, the first row about the probability of a space is available comes from the data that we collected. So we have that raw data. We know the probability for every block. So we compute this absorbing chain, and we get results like this. So this is real results for Fisherman's Wharf. And let's look at the dark blue here. This is the average number of blocks that you had to cruise before you could find a parking spot. The orange here is the probability that when you arrive at that block, that there's no space available. Okay. So for every so this is aggregated up to neighborhood level. But for every block, we can say back out what's the probability that when you show up there as a user that there's a space, and what's the probability that when you show, we also say what's the average number of blocks that you have to search before you can find an available space. So that's sort of all driven by the empirical data and this simple queuing model. Okay. And we can do that for various neighborhoods. And so this is the so-called marina neighborhood. And it turns out here at 6 o'clock is when the meters turn off in San Francisco. All right. Well, actually, it turns out they probably shouldn't turn off because there seems to be a lot of demand, potentially in the evening. So let me move on. So, okay. So the first part, this first part was really about how do you compute the relevant quantities that we want to use in evaluation. So like I mentioned, so this program, SF Park, we changed the prices on lots of blocks. And then we want to evaluate whether or not it reduced the amount of time the amount of time you took to find a parking spot. And we want to know, did it also reduce the occupancy? You know, did the blocks move into this 60 to 80% range? Okay, but before we could evaluate that properly, we had to create some tools from queuing theory that those are quantities that we're going to use in the evaluation. Make sense? Okay. When is this over, Bill? I'm just trying to, because we started at 4:30, right?
Yeah.
Okay, this is that. Okay, good.
Like 4:35. Yeah, I'd say
About 10 minutes. Okay. Okay. So the next part is really sort of econometrics or statistical evaluation. Okay. So let me just, this is a big picture. Okay. Let me show. Okay. So these the columns represent here 10 different price changes. So we had this evaluation time period. So roughly about 6 weeks between each price change. So this is 10 price changes, but we took baseline data before we did any changes in price. Okay, now what I want to show you is that look at in the top row, at the top, the green. So we wanted to push the occupancy of blocks into the 60 to 80% range. All right, so the top is the control area. And so the percentage means, like here, roughly 40% of all the blocks were in the range that we desired. That's how you read this. Now, at the bottom, these are all from the pilot area. This is where we actually did the interventions. Okay. And so the idea was that we want to push more and more into this range. So it started about 34%, 32%. Okay, but it ended like 36. So you say, did it do anything? You know, maybe it didn't. Maybe people were too inelastic. You know, did it work or not? All right. But then you also look at the control area. So what we wanted to do is try to make a rigorous comparison between, you know, did the program, can you attribute to the program an increased number of blocks in this range? Okay, so what we did end up doing this is that we kind of built, we want to look at a couple things. One, the first model is really about how many percentage points by which a block deviates from the range. So 60, 80% is the range that we care about. If an occupancy of a block was, say, 85%, then that would deviate by 5 points. Okay, that's the first dependent variable we care about. And the other thing is the number of blocks cruised. Okay, so what we want to make sure is that we're pushing more blocks into this. We want to decrease this deviation from the range over time, and we want to see if it decreased the cruising. Now, the key thing that we care about is the program. So how many times did the rates change for a given block? Okay, now there's lots of other factors that contribute to occupancy and parking demand. So the so-called like neighborhood effects. So there could be things occurring, say in the Fisherman's Wharf area that could have happened that we don't, maybe, for example, we may not observe things that could happen. A parade came through, or they shut down some streets in that neighborhood, unobserved characteristics. And also those kind of things that happen at the block level, right? So maybe some of the meters were disabled, but we didn't observe it. So we want to be able to sort of control for a lot of some of these unobserved factors, okay? So what we do, oh, well, maybe this, let me go here first. So what we end up doing is number 1, 2, and 3 relate to the occupancy, okay? And what you want to look at, what we really care about is these number of changes. So every time the price changes, what happens to how much close do you get closer to that range? So a negative means that every time the price changes, you get blocks are getting closer to that 60 to 80% occupancy range. Okay, and this is so-called panel regression. So we look at one block over many time periods. Okay, so we have a lot of observations from one block, and so you have to take into account. So we take into account time of day of week, we have lots of data, so we can sort of control for a lot of these factors. So basically the bottom line, these first 3 models basically show that when you change price, let's say these first 2, that when you change the price, you are actually moving closer to that range, but it's really tiny, it's really small. And over here, 4, 5, and 6 are really looking at cruising. So every time you change the price, are you decreasing the amount of distance that people have to search to find a space? Okay, and I'll claim here that the answer is yes, and it's going to be significant. Let me show you something though. So, and this relates to your question, that here are all the 10 price changes, and the y-axis is sort of the percentage change that you're moving closer and closer to the target. So it turns out that early, and the blur there is sort of the confidence intervals, all right? And so you can see early in the program that it's sort of indistinguishable from 0, that maybe there's no big effect, but as you continue to change the prices, you actually that's when you get the impact. So we continued this out for 20 time periods. So this program is still in effect now. It was a pilot, but now it's been scaled up citywide and so forth. But the point is that it takes quite a while we can interpret this. It took a while for people to actually respond, that we can say people responded to this program. Okay, it wasn't until maybe much later that we can feel confident to say that this program changed people's behavior. But by a very small percent, maybe 2 percentage points on occupancy, okay? But, and the same thing here for cruising, you don't start to get an impact until much later on in the program. So it turns out that even though the average occupancy only changed about 1 to 2%, the corresponding change in this cruising was around 50%. So it really decreased the amount of time. Even though there wasn't a lot of cruising at the beginning, we can attribute about 50% of the decrease in the amount of time you were looking for parking to this program. And to provide more color, so this is the map of San Francisco. It actually turns out that of the roughly 500 blocks, only about 43 of them accounted for about half of all the cruising. So we kind of know this. There's like popular areas in the city that basically generate most of the searching. So it's very localized. And so this is very surprising. Well, in some ways, that it turns out in this program, we were changing the price on roughly about 500 spaces. But we can get close to the same, well, I don't want to say. It actually only turns out that about 43 of the blocks are generating most of, half of all the congestion. And I think this phenomenon kind of holds. And that kind of makes sense to us, like Nassau Street, okay? If you get Nassau Street right, then you're really going to get a big bang for your buck. Yeah, and so there is a lot of just evidence that, when you turn the meters off at 6 o'clock, you really get this big spike. So people are just waiting, to park. Once the meters turn off, then you get a lot of this demand. So the prices are doing something to sort of control demand because, why else would there be this sort of really big discontinuity at 6 o'clock? So there's something happening there. Good question. So like Fisherman's Wharf is not residential, but here's like residential parking potentially. That's good. So let me just kind of move a little bit faster. So like I said, let me just summarize here that this is we sort of did this field experiment to try to understand how this spatial pricing works. And I think the takeaway is, I call it like a little change goes a long way, meaning that the occupancy didn't change a lot, but the cruising, we can attribute to say that did change pretty dramatically in some nonlinear way. We got the very variety of responses spatially. Yeah, maybe the program hasn't run long enough to get smooth kind of spatial prices or not in an equilibrium, but that's not quite what we're seeing. And then we would kind of really argue that this average occupancy is something that was in the literature and something that city planners really that's what the main focus. On average, how full is it? But we tried to make an argument that really you want to try to look at from the person's driving perspective. What's the chance that you get a space? Yeah, so that's more about that. Let me just stop here. Okay, so from the implementation side, so this program, it turns out that it was sponsored by the Federal Highways Administration. And the program actually led to replication in a lot of cities. Not just in the US, but around the world have implemented, based on lessons learned here and other things, that implemented versions of this time of day pricing. They tried to use some of these principles. So so we did a big roadshow in a lot of different cities in the US to try to replicate this to a lesser degree. Here they put sensors in every single parking space. There were 6,000 spaces. They put an individual sensor in each space. It's very expensive. So there's a very lightweight, light hardware versions of this that don't use as many sensors or don't use sensors at all. Maybe use cameras, maybe use parking meter receipts to try to infer availability, but there's certainly asset light versions of this because this program is very expensive. It was a $20 million program. It was matched $20 million from the state. So a $40 million program that a lot of cities and states don't have that money. So a lot of the work has been about how do you translate this to other places. And so, of course, this now may have more resonance if you look towards, this is my editorializing now, towards AVs, autonomous vehicles, or self-driving or driverless vehicles. Those terms aren't all the same, but if people want to ask me about them. So certainly that has parking. There's arguments that actually these vehicles won't park themselves. In fact, if they're privately owned, which could be a disaster, they would just drive around in circles on the road. They have an incentive because they may run on electric motors that are quite efficient at relatively low speeds. So the idea you might actually have vehicles, you have an AV, it drops you off, and guess what? It doesn't park. It may just drive around in circles. Worse yet, it may collude with other AVs to create congestion so they can move slow. No collusion. To collude, to actually drive slow, all right? Or it may drive back to your house and park in your garage or something like that. So this parking work that we're continuing to do, actually moving forward, we have current work that really looks at the implications for AV, autonomous vehicles. And so let me just kind of wrap up here. Thanks to people in the city of San Francisco, who we work very closely with. This is based on a set of papers that we've published on this. And I'll stop there. So thank you. Okay, we have time for a couple questions. Yeah.
So I observed that Boston was doing a similar experiment, but directly using at least one empty block on the street. That's their objective.
Say that again.
So I observed that when Boston did the same experiment, they said we want at least one block on the street most of the time, and use that as the objective. Do you think that's a better way to justify?
Yeah, so you're saying usually they want to have one available parking space per block. And that's, yeah, so that's close to the kind of objective we're looking at. If an average block has 12 to 15 spaces, if one of them, if 14 are full, then you get around 80, 85% full. So that's kind of like the similar criteria. But you need much better sensing to make sure that if there's only one space available. Yeah.
The technology question, if there are sensors that sense whether a parking spot is available, is there an app that would tell you where to go to park, the closest parking or cheapest parking?
Yeah, so the app from the city, and now there's a host of other apps that have availability information. So if you either have the app, you shouldn't look at it while driving, that's another problem. But if it's integrated into your car, some navigation system, they could direct you to the available parking space. Yeah. So the app we made was voice activated too. There.
So I'm thinking about, and I'm not advocating this, but I'm thinking about these issues when you have conflicts and allocations of resources. And some people argue that, what would a private company do if they took it over? And I'm reminded, I for the first time in a long time, I flew Southwest Airlines last week, and they have this model. And I think of their business model as being very similar to this, which is you have tiered pricing, with the goal being that you want to sell all the seats, but if you're the last seat is going to be more expensive than the first seat, right? Yeah. Did you guys look at any of the data? Because I know airlines spend millions of dollars on this type of research. What sort of models do they do and did you look at that?
Yeah, part of what Bob mentioned, we wanted the prices to be transparent. And so if you do this sort of inventory-based pricing, it's much, as opposed to airlines, you go to buy a ticket, you don't know how much it's going to cost. That's one thing. But if you go to park in the city and once you park, you get out and look at the meter and it's, $100 an hour, that's not a satisfactory political outcome. So a lot of it's political constraints. So yeah, that's why we didn't go that direction for it.
Yeah, Bob?
Well, now that you finished with San Francisco, I'm just wondering if you applied this to La La Land.
Where is that? Oh, La La, okay. Now, I would say here in San Francisco, part of any additional revenues that will be generated from this program go to improve transit and go to improve the BART. That's the subway. At Muni. Because otherwise, if there's no alternative mode, then the pricing now takes on another different character. It's certainly, and you have to think about equity impacts of this kind of for a public good. So the way San Francisco got around this is that any revenue, goes to improve transit, and transit's for everyone, and there's subsidized transit passes and so forth. So you just don't end up with like BMWs parked on the street, which
You don't have people singing on the street.
Exactly. Yeah, so that's a big deal when you're implementing in other cities. Are there viable other modes, or are you just really gouging? And let me just say one of these programs make it easier and more convenient to park. And for some cities, that's not the objective. That makes it easier for you to drive your car. And actually, in some ways, that works counter to a lot of cities' sustainability goals. Okay, so we're sort of torn with this, like we're doing this program, it makes it easier for you to drive and more, but guess what? That may not be the right objective to actually go after. So we're working on that also.
Well, I have a little more technical question, guy, where you took the logarithm
Oh, yeah.
of the probability. Was that more just for computational convenience, or because log of probability sometimes an interpretation of information?
Yeah. No, it was mainly for computational convenience to get sort of a nice linear regression.
But I just wondered if this
That's a good
have
point.
some sort of information theoretic consequence. But
Maybe not. Yeah. So log over probability. Yeah. You maybe get the entropy negative of that. Okay.
Any more? Before we take Robert, as you mentioned, there'll be a reception back in Sharon on the